Hello, everyone. Welcome to this new webinar, Integration of Phase 1 Aerial Cameras with Inertial Systems. Thank you very much for attending this morning. I'm going to introduce myself. I'm your presenter today. My name is Luis Viveros. I'm America's Technical Sales Manager at Phase 1 Industrial. I'm bringing this webinar to you from the U.S. office of Phase 1 Industrial at Rocky Mountain Metropolitan Airport at Broomfield, Colorado, USA. This morning, or this afternoon for someone, I will bring to you some concepts related to all the steps required to trigger the camera, how to orient the camera, how to connect the camera to inertial systems, and how to retrieve the information coming from those inertial systems. Basically, we have 4 sections today. The first one is understanding the trigger and mid-exposure pulse workflow and GNSS IMU message tagging. The second will be the setup for camera to inertial measurement unit orientation. And the third will be IMU and GNSS antenna lever arms measurements. And the fourth will be image metadata and pose positioning and orientation systems data sequence matching. Okay, so here we go. Let's start. So the first thing is understanding what is the trigger timing, what is system ready and shutter actuation, what is mid-exposure pulse timing, post-event tagging, trigger and mid-exposure pulse signal direction, as well as GNSS and IMU message direction. As you can see, we have a diagram of what the integration of the camera may look on a system with a flat management system connected to it, and an inertial system or the POS, which consists of a IMU, a GNSS, and an onboard computer. We have 2 terminals in the camera, N and B, that we will explain the usage for them in a few minutes. And then let's go for the trigger timing. As you know, as some of you may know, some of you may be expert on this, some of you may not. The flash management system can send a signal to the camera, either to the IXU or the IXM. This signal consists in a 5-volt falling edge pulse. For the actuation to happen, a few things might need to happen. One of them is the trigger. The trigger nature would be, as I say, a falling edge signal, 5 volts, with a drop time of not be smaller of 1 microseconds. If you can see the image, you can see some lines that represents the pulse, the signals. So for the trigger in, we see at the very first beginning the dropping of the signal from 5 volts to 0. So this is the signal that might last at least 1 microsecond, the drops, excuse me, and the pulse width might be at least 2 milliseconds. Why is that? It's because we have a system-ready signal that can only be secured or can be initiated after 2 milliseconds. So if you see the first line showing the trigger, it's showing the trigger in with pulse longer than the timing 1. Here is 2 milliseconds for the system ready, and the triggering pulse width is a little bit longer. So we have that the complete cycle of the shutter of the camera will last for different series 600 milliseconds for the IXURS 1000 or IXURS 1900, which is what you can see in the documentation at 0.6 seconds as a cycle rate. For the IXM 150 is 50 milliseconds, which means 2 frames per second. And for the IXM 50 and for the IXM 100 is 330 milliseconds, which can be translated into 3 frames per second. So once we actuate the camera, the trigger will shutter. So as you can see, the time T2, will be the timing for the mid-exposure pulse to occur. The mid-exposure pulse is a signal that is sent by the camera by the time the half of the aperture of the shutter occurs. So for the IXM 100, you will have approximately the timing of the mid-exposure pulse since the beginning of the actuation, which means, since the beginning of the trigger, will be approximately 30 milliseconds plus half of the exposure time for the IXM 100, 20 milliseconds plus half of the exposure time for the 150, the 190, and the 1000s. So the mid-exposure pulse timing, which is the second half of the aperture of the shutter, will be approximately half of the exposure times plus 1.1 milliseconds. So all these details tell us something. You can see in some inertial systems that you have a shift time for the pulse. For the phase 1 aerial cameras, that shift time is not necessary. The camera is returning the mid-exposure pulse at the exact moment of the mid-exposure. So there is no need to calculate a shifting time since the starting of the actuation of the trigger. Okay, so we have now the position and orientation system, POS, event tagging, which basically records navigation data generated by the POS and the event time generated by the camera, specifically the mid-exposure pulse coming from the camera. These two informations of this group of information is necessary for post-processing and orienting the frame of the camera, of every frame of the camera. So basically, the mid-exposure pulse signal is recorded as a sensor event, plus the navigation solution, also called aided inertial navigation solutions, that contains time, either UTC or GPS time, contains position, latitude, longitude, altitude, contains also attitude, roll, pitch, heading, and some other information like track, velocity, speed. All this information, with the exception of the sensor event, is part of what is called aided inertial navigation solutions. It is not just the IMU working, but it's a assisted IMU or assistance system that is blending information of the IMU and other sensors like the GPS. So the navigation and the event time are recorded into the navigation log of the POS. The event time message is parsed and sent back to the camera. So the event ID and the event time, or the event mark of the mid-exposure pulse, is embedded back into the message and send it to the camera. So for further purposes, post-processing will use the smooth best estimate of trajectory to calculate camera position and attitude angles interpolated from this bed. This is necessary for the generation of the exterior orientation for events or frames, whatever you want to call it. So again, and to reiterate and understand the directions and the workflow of these signals. First of all, let's remember the trigger and the mid-exposure pulse, the very nature of these two signals is electric. It's not a pass message. It's not a signal, a serial message like it would be the GNSS message. So we have the input coming from the flight management system to the camera, which is carried by the purple wire through the pin number 4, as you have seen our documentation. So the mid-exposure pulse is returned to the POS, to the post system through the white wire or the pin 7. So it's a very simple workflow coming from the flight management system and returning not to the flight management system, but to the POS. I have ignored, or I have not included, of course, the grounding of this circuit for benefit of simplicity. But you can see that the last two 9 and 8 pins, black and gray, are the ones to be connected to the common. So you have a complete trigger system with mid-exposure pulse returning that can be connected to the terminal B of the IXM or the IXU camera. Then you have, from the POS, you have the injection of a message. This time it's not anymore a signal, but a message. It's a well-known sentence coming from different systems with different structures. So phase 1 can read either a Planix, Novatel, or our partners' messages, EGI or GGS, as well as the NMA stream. This message is injected into the camera to the image through the pin number 5 or the blue wire. You can see that in our documentation that is available in the download area. So the complete workflow is now consisting in trigger into the camera, mid-exposure pulse back to the post, and from post to the camera, the GNSS and IMU message, more well known as the GPS message. So this is the first section. The second section is covering camera to aerial measurement unit orientation setup. So for these sections, we will cover 3 basic concepts. One of them is the reference body frame and the phase 1 camera entrance pupil, IMU body frame and mounting angles, and vehicle body frame. So the first one, the reference body frame, is what we call the camera. We call it reference body frame, refers the sensor, or in our case, the camera. So this system, or this reference body frame, has an origin that refers or is located at the center of the optical image, or the entrance pupil. The entrance pupil is also, as a concept, is the image or the seen image that is beyond the vertex of the angle view of the lens. So we can understand this origin as the center of the image as we see it, as a frame. Excuse me? Hello? Yes. Can you hear me? Oh, sorry for this inconvenience. Something happened with the sound. So I will come back to the beginning of this. So as I was saying, and sorry for the inconvenience again, camera to inertial system measurement units, first concept, reference body frame, and phase one camera entrance pupil. In case you missed this, I will repeat. The reference body frame, origin, refers to the center of the optical image or entrance pupil. The entrance pupil is beyond the vertex of the view angle of the lens. So we can understand it's a virtual frame that is located somewhere beyond the vertex. And we can see it like as a landscape, and it's not flipped. Okay, so this origin is where everything is oriented to. The reference body frame, of course, is defined as a right-hand orthogonal coordinate system, which means when you have your right hand, thumb, index, and middle finger will comprise the X, Y, and Z angle, with the X axis aiming or pointing in the forward direction or the flight direction. The Y-axis will be pointing to the right of the center of the optical image, and the Z-axis will be pointing downwards. When I'm talking about downwards and right, you can see the image on the right of the presentation. It's the way we map. It's not the way someone can take pictures. It's aerial photography. So downwards is the Z angle in the positive direction, and X is the flight direction. So for your reference, all the phase one aerial cameras are well documented in the download area of our webpage, which is industrial.phase1.com. You can find all the series, all the interface drawings with the location of the entrance pupil and the mechanical details of every interface. So the next concept is the IMU body frame and its mounting angles. So the IMU body frame is defined as also as a right-hand orthogonal coordinate system. The mounting angles are the sequence of rotation of the IMU body frame to bring into alignment with the reference body frame. In other words, the mounting angles is the sequence of rotation is needed to align in angles in angular rotations to the orientation that the reference body the reference body frame has. So in this case, for example, you have a camera aiming downwards with the body frame aiming its X-axis in the flight direction, but the IMU is oriented minus 90 degrees. So the X-axis is pointing to the left. Okay, this is a simple rotation sequence consisting in only one axis rotation, would be 90 degrees to the back or to the right to align the IMU to the camera. But you can find some more complex implementations, some more complex installations. So the preference or the most recommended setup, as always, is make it simple and have it both systems aligned, reference and IMU body frames align in the same direction. When you need to rotate more than one axis, you need to refer to the Tate-Bryan rotation sequence. It might be complex because it's not the simple rotation. Z-axis first, X-axis second, and Y-axis second, and X-axis third, which means that as you start with the Z-axis, the second axis, the Y-axis, might be rotated already once. And by the time you need to rotate potentially the X-axis, you might be rotated this axis twice. So the rotation sequence, the Tate-Bryan rotation sequence, is a convention to all of us to follow and rotate and align the IMU in the consistent way. Okay, clockwise rotation is positive, counterclockwise rotation is negative. So finally, we have the third concept, and this might sound trivial, but it is useful at some extent, at some point. The orientation of the vehicle body frame is with its x-axis towards flight direction, which is called the longitudinal axis, the y-axis toward starboards or to the right is the lateral axis, and z-axis downwards, again, vertical axis. It is most used to measure the distance between the GNSS antenna and the camera origin, or the entrance pupil, or the reference frame origin. We don't need to have a point, an origin for this vehicle body frame, as long as we have it as a reference where to measure. So we will not, later on I will explain, the antenna or the antenna face center needs to be measured for lever arms purposes to the origin of the body frame, to the reference body frame. But we are not using the reference body frame system, but the vehicle body frame. That's why we need to know this. Okay, third section, IMU and GNSS antenna lever arms measurements. So first concept, how to determine the entrance pupil location. I believe this is a question that most people that have contact with the phase one IRL cameras have this question. From the mechanical standpoint, you will see that it's easy to understand, but sometimes it's not easy to implement. So we have some tips for that. Also, the reference frame origin to IMU origin lever arms, and the reference frame origin to GNSS antenna lever arms. We will explain some concepts here. So how to determine the entrance pupil location? First of all, the entrance pupil location is not determined like as a physical mark in the camera. So we need to calculate that. As I said before, in the download area, you can find the interface documents for the camera, for every camera. So you can find a table with explicits the distance between the mount plane and the entrance pupil for any given lens, which are determined or what a specific focal length. The mount plane or the camera mount is the plane where the camera will be attached. There are all the cameras and different dimensions have 4 mounting threaded holes. So you can see in this case that for this camera, that might be the IXM 100 with an 80 millimeter lens, you will find that the distance from the entrance pupil to the camera mount will be 69.1 millimeters. Okay. Again, as we explained before, being the origin of the reference body frame, the entrance pupil, and the Z-axis having positive direction, downwards or aiming to the ground, you can understand that this distance from the entrance pupil back to the mounting plane will be and must be considered as a negative measurement. Okay. The same happens for the X and Y values. The distance from the entrance pupil can be usefully or can be served by the location of the mounted threaded holes, the mounting threaded holes. So if you see the documentation, you will see the distances on the blueprints. So to understand this and to make the right calculations, you need to see the camera from the back as if it was our top view. And in a sort of X-ray, you can see the measurements of the entrance pupil to the mount holes. Okay, so in this case, as we see the back of the camera, we can understand that any distance from the entrance pupil in the forward direction, or in this case, in our view, up, but this would be the forward direction, would be positive. So for X, a forward distance from the entrance pupil to the mounting holes must be computed as positive. And a backward distance from the entrance pupil must be computed as negative. The same for the Y-axis. Right represents positive and left represents negative. So any calculation to a well-known point can be used any of these 4 mount holes, but you need to consider the direction of the value, or if it's positive or negative. Either you consider the lower right or lower left mount holes to be your reference in your mounting frame, and from there to measure the distances to the IMU origin, which we will see the next step. So the reference frame origin to IMU origin lever arm. This can be sometimes challenging, but if you consider all these measurements, you can see that it's not that difficult. So first of all, the distance of the IMU body frame origin is from the reference body frame. In other words, the distance are measured from the entrance pupil to the origin of the IMU, and not the other way around. So for X, a forward distance from the entrance pupil to the IMU origin must be computed as positive, and a backward distance from the entrance pupil to the IMU body frame origin must be computed as negative. In this case, we can see that the distance between the IMU and the entrance pupil is positive. Okay, because the X axis of the camera is aiming forward, and the IMU is receded or is displaced to the front. Same happens with the Y-axis. The distance from the IMU from the reference is positive. And in the case of the Z value, we can see that the IMU is above the entrance pupil, above the camera, above the origin. So any distance between the origin of the IMU and the origin of the entrance pupil must be computed as negative in this case. Basically, I would say most of the cases for the Z axis will be negative because the IMU might most likely be located somewhere up, somewhere in inside the system, not close to or underneath the camera. So finally, the reference frame origin to GNSS antenna lever arms we have is a distance of the antenna face center from the reference frame origin, from the entrance pupil. So it is measured in the vehicle body frame along the X, Y, and Z axis of the vehicle body frame, not along the X, Y, Z angle axis of the camera or the reference body frame. So for X, a forward distance from the entrance pupil to the GNSS antenna face center must be computed as positive, and backwards will be negative. For Y, a distance from the entrance pupil to the right means positive, and a distance from the entrance pupil to the left computed as negative. For Z, a distance from the entrance pupil downwards must be computed as positive. It's rarely because you will put the antenna up there. So you must most commonly have a distance from entrance pupil upwards the GNSS antenna face center as a negative value. Then the fourth section, and the last one, image metadata and post-data sequence matching. So we have three concepts here. One is the GPS receiver setup in IX capture, EXIF metadata coming from the post system containing GNSS IMU, and the differentiation of event-driven messages versus continuous messages coming from the post, and how this can help us to understand the matching of the events with the file names. So, as you see, which is not familiar, this gray rectangle is part of the interface of IX capture during acquisition setup. You can select several GPS receiver options. The basic or the first one would be NMAA device, which will set up the camera to receive NMAA stream coming from the POS, but it will not be related to any event. It will only represent a timing and a position that was allowed to enter and to be stamped into the image in a period of time of 1 second. So no event ID or no event time is present in the image metadata or the EXIF log. The EXIF log, just to be more precise, is an automatic comma-separated value file, CSV, being generated or being recorded by the time of acquisition, along with the images in the computer repository folder. It's something that today you will not choose. It's a file that will help you to understand what is the recording of the images. So you see in the figure below an excerpt of what would be a EXIF log recording. So for the NMAA option, you have no event ID, as you can see. So it's no counting of the images, of the time marks in the navigation. Excuse me. Despite the fact that you might be recording the event mark in the navigation on the post system. But this is, please remember, this is the message coming back from the post being stamped or injected into the image. So for this case, when we select NIMA device, having all the camera wired from the post, we are not obtaining an event ID. Neither the GPS time that we can see in the image below belongs or have any relation with the mid-exposure time mark. Okay, it's something that we can make an analogy of the camera opening the logic gates to receive any sentence during 1 second. But this message is not responding to the mid-exposure pulse or the trigger mid-exposure pulse workflow, okay? So no GPS event, which means we have longitude, latitude, and altitude, pitch, roll, and yaw, but those values belong to what we called before the aided navigation solution, aided inertial navigation solution. It is a sort of a real-time solution. It is not as accurate as we might want for the generation of exterior orientation and post-processing of the images themselves. So we have a sort of dilemma here. We don't have GPS event, and the information we have is not good enough for photogrammetry purposes. Okay, so which are the other options? Any other of the GPS receiver options will bring us will be known as the event-driven option, either Novatel, Planings, EGI, GGS. So in this case, the event ID and the event times will be present in the metadata in the image and the EXIF log in the folder repository of the images. So longitude, latitude, altitude, pitch, yaw, and yaw are not transmitted because the system is only concerned and busy marking the mid-exposure pulse time mark in the navigation and returning a message with the sequential number of that event and the GPS time when that mark occurred. Two formats, of course, GPS time and weeks of second. This is accurate. This is the actual instance where the event happened, meaning event, meaning mid-exposure pulse mark time. Okay, image position and attitude in an accurate way, for this case, can be obtained after post-processing, but not at this time. Okay. The upside of this is that we have file names that we can have any convention during the setup of the acquisition in AXCapture, but we also have a GPS event ID that can be connected to the navigation post-processing data. So the number in here, 20, 21, 22, 23, will be recorded with the same number, and any post-processing will have position and attitude calculated with accurate manner. And finally, event-driven options, which some cases, some systems comes with what is called real-time option, which means it's a combination of the GPS event with actual GPS time, but also with longitude, latitude, altitude, pitch, roll, and yaw, coming from the aided inertial navigation solution. It's still not post-processed values, but helps in case during the processing workflow you need or you may want to have the images geolocated, which is slightly different of saying that the images are georeferenced, which they are not. It's just a tag, a position tag, an attitude tag for ancillary purposes, but they do not represent an accurate position or an accurate attitude for photogrammetry purposes. Very well. This has been the presentation. I will ask if you have any questions, and if you have, please type in. I will try to read them and respond accordingly. Let me see. Seems that there are no questions so far. So I will have to thank you all for attending this presentation. Thank you very much, and have a great weekend and great holidays. Thank you all.